Hi, this is Lauren Kong, and I'll be doing problem number 71. A ball launcher in a pinball machine has a spring with a force constant of 1.2 newtons per centimeter. The surface on which the ball moves is inclined 10 degrees with respect to the horizontal. If the spring is initially compressed 5 centimeters, find the launching speed of a 0.1 kilogram ball when the plunger is released. Friction and mass of the plunger are negligible. So they give you a figure here, but I started out drawing a free body diagram. So my free body diagram was first in the event A. The first event is that it is compressed, so it doesn't have any kinetic energy. It just has the spring potential. There's a 10-degree incline, and technically, there is, I guess, potential energy if you wanted to make the ground where the spring starts 0. But since I didn't want to calculate that, what I did was I just put the potential energy of it for the gravity as 0. So I just had this as 0, and then whatever it increases, that will just be increased from this line. So that's event A. Event A is when it's totally compressed and it's just stagnant. Event B is when it's at equilibrium. The spring is completely at equilibrium, so there's no more spring potential energy, but now all of that energy is transferred to kinetic energy of this ball. And that distance is 0.05 meters because it was compressed 0.05 meters. So then if you release it, it lengthens out to 0.05 meters. And so we can also find what the potential energy is of here because we have this as 0, and so all we can do is just have this triangle, 0.05 meters. We know it's 10 degrees, so that means that the sine of this is this. So we also know from the given that the force constant is 1.2 newtons over centimeters. I converted everything to meters to make it easier, and the spring compresses 5 centimeters or 0.05 meters. So what I did was I started conceptually. The energy in this situation is going to be the energy in this situation. So the energy of A equals the energy of B. But most specifically, what are these energies? So the energy of A, we just have the spring potential. So that's just U of S. That equals the kinetic energy of B because at this now event, it is moving. It is going at a speed, and that's what we're finding. And then also it has gravitational potential energy because it's above the line that we previously marked as 0. So now I just solved. So with the formulas, 1/2 kx squared, which is 1/2 of, because I've converted everything to meters, 120 newtons over meters times 0.05 meters squared equals the kinetic energy of B, which is 1/2 meters velocity squared. The velocity is what we're trying to find in the end, plus the gravitational potential energy of B, which is mgh. I found H specifically, as you look here, that's just this. That's this little part here. And so after you plug this all in, you find out that 0.15 joules, that's the energy of the A, so the potential, the spring energy here, equals this, which is the kinetic energy of B, plus this, which is just the potential energy, it's just the height here. And then if you solve it, you isolate the variable of V squared, you get 1.68 meters per second. So that means that at this moment specifically, when the spring is 0.05 meters, when it's at equilibrium, and it's this specifically, it's this above the previously demarcated line of 0, it is going at a rate of 1.68 meters per second.